Well, we're going to skip ahead in our PowerPoint notes a little bit to Roman numeral section 4. So please find that section. It would be helpful if you had handy your calculator. And also there are two worksheets that pertain to this section, one of which we could start tonight if you'd like, or also you can work on them in class. But one of them says molarity review sheet, and the other one has problems that says molarity and molality on one side of a worksheet. So there are many ways by which you can measure concentration. You can find the percent by mass, the mass of the solute divided by the total mass of the solution. You can find percent by volume, the volume of the solute per volume of solution, and both of those you turn into percents by timesing by 100. The most common way is the third one down, molarity, which you should be very familiar with, moles of solute per liter of solution. However, we will learn about molality in this particular section because we need a way to measure concentration that is not impacted by changes in temperature. And I will discuss how easy it is mole fraction problems are to do in a bit later on. So first of all, make sure you know what's the difference between concentrated or dilute. Concentrated would be you reach for a can of frozen orange or grape juice and you dilute it out by adding a certain parts of water per part of frozen concentrated juice. So for example, if you're making frozen grape juice, if you have 4 parts of water to 1 part of grape juice, I'm not sure I agree with that. That would be 25 parts per 100 or 25% grape juice. I disagree with that math. I would say that was 20%. But regardless, I'll check that. You can express it as a parts type of concentration. In your soft drinks, apparently there's some phosphoric acid in soft drinks. There's also carbonic acid in soft drinks. So in dilute concentrations, these aren't a problem, although I wouldn't drink a lot of them because it's hard on your teeth. So you can do something that's called a serial dilution, which you may be familiar with. And that's where you start off with progressively, or you start with a concentrated solution, as indicated here with the very dark color, and you make it progressively more dilute, as indicated with the light color. So notice what happens as you go from 1 milliliter of stock solution, you add it to 9 milliliters of water, and now you're only 1/10 as strong as what you originally were. You repeat that again, take 9 milliliters of the diluted part to 1 milliliter of the diluted out part to 9 milliliters of water, and now you'll have 10 milliliters of 0.01 concentration of whatever it was you started with. You've gotten 100 times more dilute. Do that one more time and you've reached what we call parts per thousand. You've diluted it out in a serial dilution 3 times such that you're 1,000 times less concentrated than you previously were. Well, parts per thousand and sometimes parts per million and parts per billion are often used as units of concentration in environmental issues. So for example, if you did this 3 more times, then you would end up with parts per million, meaning 1 part of solute per 1 million parts of your solution. And parts per million, although that's a small amount, 1 in a million, it's actually kind of important because here's what can happen to your teeth if you get too much, I should say, fluoride. So we recommend in the United States that people get about 1 part per million of sodium fluoride. The fluoride is what's important to prevent tooth decay. You get bigger than 1 part per million and your teeth look like that. Not something that's going to get you the prom date. So I think they called that the brown stain disease. So not enough fluoride, you get cavities. Too much fluoride, your teeth look funky. And that's in very small parts per million. Believe it or not, this goiter was once considered extremely attractive in medieval times. Having a large swollen neck apparently was supposed to be attractive. You got me. But the way you prevent this goiter, which is an enlargement of your thyroid gland, is you make sure that you get enough iodine. So 5 to 20 parts per million of iodine will prevent your goiter from forming. Where do we get our iodine? Look very carefully at a salt large salt container, the kind you buy from the grocery store, you'll see that most of them say iodized salt, and that's where in the United States we get our iodine. They add it to the sodium chloride. So that's an enlargement of your thyroid gland. Lovely. Plus, if you look at it, the guy looks like he's wearing a wife beater shirt, so it doesn't get better than that. Also, parts per million matters if you want to swim in a swimming pool that stinky little kids have been in. You only need half a part per million of chlorine in a swimming pool to kill bacteria, and I guess they go 2 to 3 parts per million for typical large commercial swimming pools. That's a good thing to know. If anyone's ever been a lifeguard and has watched little kids in the pool, they don't always shower when they get in the pool. Now we're going to take a moment and take a break from this particular PowerPoint to watch a very short video about how one can prepare a specific molarity of a particular solution. So let's take a look at this for a moment.
Copper 2 sulfate pentahydrate is added to the balance. The mass of 1.934 grams is noted for future use. The copper sulfate is then carefully added to the 100 milliliter volumetric flask. Distilled water is added to bring the solution level up to the mark on the neck of the flask. The flask is shaken carefully to dissolve all the solid. What is the molarity of the solution? First, calculate the number of moles by dividing the mass by the molecular weight. Next, calculate the molarity by dividing the number of moles by the volume.
Now, the thing that I'd like to point out about this is that if you go back and think of what they didn't add 100 milliliters of water. They put in a specified amount of copper sulfate and then added the volume up to the specified volume line. So if you're going to make a 1 molar solution, you figure out how much does 1 mole of your substance weigh, add that amount to your container, and add water up to the 1 liter mark. You don't add 1 liter of water, you add enough water to make the total volume equal 1 liter. So this is how you do molarity problems, and you hopefully have remembered this from the past. You have a review worksheet called, I believe, Molarity Review. And on that particular worksheet, if you can read English, I will walk you through how to do molarity problems, and they're quite simple. So molarity is measured as the number of moles of solute per 1 liter of solution, not per liter of water. It is the most common unit of measurement for concentrations in chemistry. And here's an example with using sulfuric acid. You find your moles of sulfuric acid by going to the periodic table and getting the molar mass. I've got 2 sig figs in that beginning number, so that's why I have 0.050 moles of hydrogen sulfate or sulfuric acid. Next, it has to be per liter, so always, always, always change milliliters to liters. So that would be 0.250. You can go through these steps if you'd like, but it's much simpler if you just take the milliliters and go 1, 2, 3 places to the left with the decimal point. Finally, you simply take your moles divided by your liters and calculate your molarity. Big capital M. Please don't get lazy and put a little m. You'll see why in just a moment. So that's a 0.20 molar solution. And the beauty of molarity equations is that if molarity is moles per liters, you can solve for moles, liters times molarity, or you can solve for liters, and that would be moles divided by molarity. So if someone says how many moles of potassium nitrate are in 300 milliliters of a 0.50 molar solution, change milliliters to liters and multiply it by the molarity. Now here we've written the molarity out as moles per liter. That way liters cancel and your answer will come out in moles. Probably we were a little sloppy. There's only 1 sig fig in 300 milliliters, but I think that's just because the teachers got lazy. So we have 0.15 moles in that particular solution. So you have a worksheet entitled Molarity Review. You also have the back side of a worksheet. One side says colligative properties, the other side says molarity and molality. Knowing what you learned in first semester and what we've reviewed now, you should be completely able to do molarity problems. However, the problem with molarity is that it involves putting, let me back up, the volume on the bottom. And if the temperature was to change, you know that as temperatures increase, volume expands. So if I had a situation where the temperature was changing and the number here on the bottom got larger, then the molarity would be artificially smaller. So let me repeat that. Molarity is sensitive to changes in temperature. Chemists needed a way to be able to calculate a concentration value that was not sensitive to temperature. And this is your new guy. This is small letter m. Molarity, capital letter M. Molality, little letter m. And the reason why we have moles of solute per kilogram of solvent is that the mass of a solvent isn't going to change, assuming you don't boil it away. Just like a hot brick would weigh the same as a cold brick, 1 kilogram of cold water weighs the same as 1 kilogram of hot water. So the volume will change, but the mass will not. So molality is still moles of solute, but simply change the denominator to be kilograms of solvent. The only tricky thing in molality problems is that instead of giving you kilograms of solvent, they might give it to you in grams. So you would have to divide by 1,000 or possibly do some sort of calculation involving density. So here's a simple molality problem. Calculate the molality, small letter m, if you added 4.5 grams of sodium chloride to 100 grams of water. 4.5 gets changed into moles. 0.077 moles of salt is what you have. Then my 100 grams of solvent has to be changed into kilograms. Once again, you could simply divide by 1,000 or go 1, 2, 3 places to the left. Finally, moles over kilograms is 0.77 little letter m, or we say that in English, 0.77 molal. Once again, we use molality because its value does not respond to changes in temperature. Okay, that's it for now. You will be having a walk around on molarity and molality, probably on block day. Take care until the next time.